An electronic calculator is a small, portable electronic device used to perform both basic operations of arithmetic and complex mathematical operations. The first solid-state electronic calculator was created in the 1960s, building on the extensive history of tools such as the abacus, developed around 2000 BC, and the mechanical calculator, developed in the 17th century. It was developed in parallel with the analog computers of the day. The pocket-sized devices became available in the 1970s, especially after the first microprocessor developed by Intel for the Japanese calculator company Busicom. They later became commonly used within the oil and gas industry. Modern electronic calculators vary from cheap, giveaway, credit card-sized models to sturdy desktop models with built-in printers. They became popular in the mid-1970s as integrated circuits made their size and cost small. By the end of that decade, calculator prices had reduced to a point where a basic calculator was affordable to most, and they became common in schools. Computer operating systems as far back as early Unix have included interactive calculator programs such as DC and Hoc, and calculator functions are included in almost all PDA-type devices. In addition to general-purpose calculators, there are those designed for specific markets. For example, there are scientific calculators which include trigonometric and statistical calculations. Some calculators even have the ability to do computer algebra. Graphing calculators can be used to graph functions defined on the real line, or higher dimensional Euclidean space. Currently, basic calculators are inexpensive, but the scientific and graphing models tend to be higher priced. In 1986, calculators still represented an estimated 41% of the world's general-purpose hardware capacity to compute information. This diminished to less than 0.05% by 2007. Design. Input. Modern 2016 electronic calculators contain a keyboard with buttons for digits and arithmetical operations. Some even contain 00 and 000 buttons to make larger or smaller numbers easier to enter. Most basic calculators assign only one digit or operation on each button. However, in more specific calculators, a button can perform multifunction working with key combinations. Display output calculators usually have liquid crystal displays as output in place of historical light-emitting diode displays and vacuum fluorescent displays. Details are provided in the section Technical Improvements. Large-sized figures and comma separators are often used to improve readability. Various symbols for function commands may also be shown on the display. Fractions such as 1/3 are displayed as decimal approximations, for example rounded to 0.33333333. Also, some fractions such as 1/7, which is 0.142857142857114, can be difficult to recognize in decimal form. As a result, many scientific calculators are able to work in vulgar fractions or mixed numbers. Memory calculators also have the ability to store numbers into memory. Basic types of these store only one number at a time. More specific types are able to store many numbers represented in variables. The variables can also be used for constructing formulas. Some models have the ability to extend memory capacity to store more numbers. The extended address is referred to as an array index. Power sources of calculators are batteries, solar cells, or electricity turning on with a switch or button. Some models even have no turn-off button, but they provide some way to put off, for example, leaving no operation for a moment, covering solar cell exposure, or closing their lid. Crank-powered calculators were also common in the early computer era. Key layout. Internal workings. In general, a basic electronic calculator consists of the following components. Power source. Keypad consists of keys used to input numbers and function commands. Processor chip contains scanning unit. When a calculator is powered on, it scans the keypad waiting to pick up an electrical signal when a key is pressed. Encoder unit converts the numbers and functions into binary code. X register and Y register, they are number stores where numbers are stored temporarily while doing calculations. All numbers go into the X register first. The number in the X register is shown on the display. Flag register, the function for the calculation is stored here until the calculator needs it. Permanent memory, the instructions for inbuilt functions are stored here in binary form. These instructions are programs stored permanently and cannot be erased. User memory, the store where numbers can be stored by the user. User memory contents can be changed or erased by the user. Arithmetic logic unit, the ALU executes all arithmetic and logic instructions, and provides the results in binary coded form. Decoder unit converts binary code into decimal numbers which can be displayed on the display unit. Clock rate of a processor chip refers to the frequency at which the central processing unit is running. It is used as an indicator of the processor's speed. It is measured in clock cycles per second or the SI unit hertz. For basic calculators, the speed can vary from a few hundred hertz to the kilohertz range. Display panel displays input numbers, commands and results. LCDs, VFDs, and LED displays use 7 segments to represent each digit in a basic calculator. Advanced calculators may use dot matrix displays. A printing calculator, in addition to a display panel, has a printing unit that prints results in ink onto a roll of paper, using a printing mechanism. Example: a basic explanation as to how calculations are performed in a simple 4-function calculator. To perform the calculation 25 plus 9, one presses keys in the following sequence on most calculators. 25 plus 9 equals. When 25 is entered, it is picked up by the scanning unit. The number 25 is encoded and sent to the X register. Next, when the plus key is pressed, the addition instruction is also encoded and sent to the flag register. The second number 9 is encoded and sent to the X register. This pushes the first number out into the Y register. When the equals key is pressed, a message from the flag register tells the permanent memory that the operation to be done is addition. The numbers in the X and Y registers are then loaded into the ALU and the calculation is carried out following instructions from the permanent memory. The answer, 34, is sent back to the X register. From there it is converted by the decoder unit into a decimal number, and then shown on the display panel. Other functions are usually carried out using repeated additions or subtractions. Subtractions are usually carried out by using 2's complement operations, where calculators have additional functions such as square root, or trigonometric functions. Software algorithms are required to produce high-precision results. Sometimes significant design effort is required to fit all the desired functions in the limited memory space available in the calculator chip, with acceptable calculation time. Calculators compared to computers. The fundamental difference between a calculator and computer is that a computer can be programmed in a way that allows the program to take different branches according to intermediate results, while calculators are pre-designed with specific functions such as addition, multiplication, and logarithms built in. The distinction is not clear-cut. Some devices classed as programmable calculators have programming functionality, sometimes with support for programming languages such as RPL or T-Basic. Typically the user buys the least expensive model having a specific feature set, but does not care much about speed. For instance, instead of a hardware multiplier, a calculator might implement floating-point mathematics with code in ROM, and compute trigonometric functions with the CORDIC algorithm because CORDIC does not require a hardware floating point. Bit serial logic designs are more common in calculators, whereas bit parallel designs dominate general-purpose computers. Because a bit serial design minimizes chip complexity, but takes many more clock cycles.